Alright, we are back. Not sure what happened, but that's okay. We are back. Sorry for the interruption, everyone. Perhaps it was an internet glitch. Perhaps we've got a common case of internet trolls. However, we are live once again. I will know that it's working if... Oh, there we go. Got a notification. Yes. It works. Okay, hopefully this one stays for a while. Anyways, I don't really know where we left off. What I'll do for those that want to watch... From whom? Not sure. The stream went down for a moment. Just restarted it. But anyways, so basically what we'll do is I always record these on my end when we stream. So I'll just make sure that we upload the recorded archive, and you can see the whole thing from start to finish. I'm not sure when that cut out, but anywho, what I was saying is I was just walking through the components of what we're going to install in the general order that we like to install these components. And what I said is we move from the smallest surface mount parts up to the larger surface mount parts, and then get to the through-hole stuff. So should go pretty quick, like I said. We've got the soldering irons up and ready to go. We've got everything just as usual. Oh. Okay. I am now realizing. Yeah, I know. If you help me out with the pronunciation, I'll certainly try, but I don't even know where to start. QAI is that doesn't happen in English. I don't know how to handle that. Yeah. Sorry about that, man. Okay, I gotta get this set. I was doing some other boards needed a slightly different temperature, and I'm gonna need to get this off of the bench. So I've got a little FR4 coaster that I like to use. I think you've seen that before. I grabbed this a little too soon. Yes, how to pronounce. Okay, so we've got a few things that need to get installed. We're going to be starting, let's see if I can do this all zoomed in like. One moment. That's not right. There we go. That's a pretty good spot to work. So that should work just fine. Morning. It is a challenge for you. Alright, you know what I'll do? I will look up the pronunciation offline. Next stream, I'm going to get it. I'm going to go from 0 to 100. Well, at least I'll try. Morning, WTP Gaming. That's easy to pronounce. Morning. That's good. Okay. Yeah, there's nothing like the smell of flux in the morning, am I right? That's awesome. We're putting together the electronic load Proto 2 daughter card right now. It's got all the fixins to now I'm just going nuts with the it's got everything that you need to control and monitor an electronic load. Of course, everything except for the microcontroller, which is why it's a daughter card. So we'll have 4 of these that slot into the main board, and it'll get connected. Yes. My only regret this morning is that I think that about 45% of people are going to find the wrong stream, which is sad, but I also don't really know how to fix that. Okay. And then we're going to have the ADCs. I am feeling inclined to start with these ADCs just because they are the most difficult components to solder. And these are the upgraded ADCs. If you've been following the series, there's been a lot of discussion about these, about whether or not the... Oh, wait, no. These are this... Okay, yeah, here's what I did. It's the 12-bit DACs that we upgraded. The ADCs were sufficient. There was like a serial communication error that was thrown off the measurements before. I found that it got way better, and I was like, all right, sweet. But the DACs, just the 8-bit DAC was not enough. And I started looking at some of the alternate components we could put on, and turns out the pin-compatible... Good morning! Oh boy, that's another name that's hard to see. Or say. Oh man, but welcome. That doesn't mean... it just adds more to my homework. My pronunciation homework. I'm gonna do some research. I'm gonna figure it out. Welcome. Okay, we are gonna get these tiny little components on the board. And it looks slightly out of focus. Is that a little better? There, perhaps that's a little better. But yeah, I am really... I'll firm commit that. I'll get that on Amazon today. Uh-oh. Who unpacks the shop without unpacking the solder? Me, I guess. Hey, this is important. Don't forget the solder. Oh my goodness. I'm gonna get this loaded up. Alright. Sweet. Yeah. Okay. There we go. Okay. So now what I did is I just tinned a couple of those pads. The intention is to slide this component onto the little dab of solder. I wonder if I can zoom in even more. I'll give this a moment. Do transform, edit, size. Oh no. Okay, yeah, it's not really working. That's okay. Next time. So we're just putting the pin 1 indicator off to align with the silk screen. Okay. There it is. Just trying to get these reasonably centered. There we go. The 8-pin part is now installed. We're going to need a lot of this flux. And that's basically the strategy. So once this is held in place, you really don't need a lot of solder. You really just don't. All it really takes is a little bit of heat and a little bit of flux. So I'm thinking just from tinning those pads, I probably have plenty of solder. Maybe not quite. A little bit more. And basically all we're doing is we're going to reduce the surface tension of the metal with the flux, which allows it to flow more evenly between the pads. And looking at the side, doesn't look too bad. Looks like we just missed one of them in the middle there. There it is. Okay. Oh, no, I usually post the schematics in the chat. I think I forgot to do that for the stream. Hopefully I already uploaded them to our Google Drive. I will need to double check that, because wow, that would be a lot more fun to follow along if you had the schematics. Sorry about that, guys. Sorry about that, everyone. I'll get that sent out. Alright, so we got the 4 pins on that side of this ADC. Those look great. Those look great. Just got 3 more pins over here. Not quite, a little bit too much solder. There we go. Oh, perfect. 2 ADCs installed. What's that? You think I'm using too much flux? Too little? Too much? I don't know. It'll be alright. You can always clean off the board. Okay. Let me see if I can find that link for you to the daughter card. That ought to be in the chat. So I will send that out. We have, here it is. Getting the link. Okay. Too little. If you can see the component through the flux, you're doing something wrong. Oh, that's awesome. Yeah, so this isn't a paste flux. I don't even know if I could put that much flux on. This is a, I forget what they call it. It's a flux pen, but it's really hard to accumulate. We used to use a paste flux, and to be honest, I really like it. So just to give you the idea of when I know it's time for more flux, it's like you can just tell it behaves differently. It's like when you're soldering and there's not enough flux, you'll notice that it just like balls up on all the leads. You add just the tiniest little bit of flux and it just like scatters amongst all the different leads. You can tell. So it's like whenever I feel like it's like sticking, that's when I'm like, nope, something's not right. I'm pretty sure that's the link to the Google Drive for the schematic that we're assembling right now. So check out the chat on YouTube if you want to follow along. Man, gotta say, WTP Gaming, you had me all self-conscious about my flux usage. I was like, oh no, what am I doing? Oh, that's not too bad. Okay. Couple more of these parts. Got the deck, and then we're actually done with this side of the board. Can you believe that? I love doing final assembly of pre-assembled boards. It's fantastic. dare I say, it's awesome. I feel like I'm just coming in here doing 30 seconds of work and then all of a sudden it's done. Alright, get the pin 1 indicator. Oops. That makes it harder. And we switched footprints for the DAC. I used to be using the, I think it was finer pitch actually. And I switched to the 6-pin part for one reason, and one reason only. And that's because this component didn't have any electrical connections. For the one that was a finer pitch, and therefore a little more difficult to solder by hand. And I was like, wait a minute. If this is more difficult to assemble, like usually when you have a 4-pin and an 8-pin, or sorry, a 6-pin versus an 8-pin version of a part, I would expect to get like an additional analog ground versus digital ground broken out from the part, something of that nature. Something kind of, you know, you wouldn't necessarily need to do it, but it's probably better. I would expect to see those types of differences. And this one, the 6-pin had the analog and the digital ground tied together, and the 8-pin had the analog and the digital ground tied together. Sending me a surprise soon? Hopefully I like surprises. Yeah, we got a little temperature sensor over here. You know, speaking of surprises, there have been a couple people that have really just wowed me the last, I don't know, the last little bit here, the last couple weeks. People have been reaching out and sharing their projects, and one of them was this absolutely fantastic electronic load project, actually. Someone reached out and they were like, hey, I did this. Have you seen it? And I hadn't. And it was really cool. So it's just made me think that there's a lot of really awesome projects going on in our community. And I just got to say, it's awesome to see. And it makes me want to do like a featured video. Like, I know that, I think it was EEV blog. I don't know if they still do it. But every now and again, he'd go on like a sabbatical and just do like community content. And I thought that was a really cool idea. I don't know if I'd necessarily want to step away while doing that, but at least to feature. Luca, I love the enthusiasm. Love the enthusiasm. Good. I like fun surprises. If it's anything like those projects that community members have been pointing me to, man, it's sweet. I love seeing that stuff. I am continuously just shocked and amazed at how talented y'all are. Wow, yeah, these are going to need way more flux. I don't know if you can see that from your view, but these pins look, or maybe I need to heat up the board. I don't know. They just look not great. These solder joints look not great. Well, that looks worse. Shorting all the pins together is definitely worse. Yep. I think that for this particular component, preheating the board a little would have done us a lot of good. Alright, we'll get the solder wick, get some of this extra metal out of here. Try that again. I don't think we need to take much off, just a little. That ought to be about right. Okay, that should be fine. These are little 3-pin. I really like these chips. I think this is one of the key changes between the Proto 1 and Proto 2 design. These little ICs are actually little isolated power supply drivers. And I think they're probably pretty similar to what's in the Meanwhile bricks we were using before. So WTP Gaming. Yeah, I wanted to zoom in a little more, and here, I can do it. It's just gonna take... Oh, we're doing it live, folks. We're doing it live. Oh, man. This is quality streaming. Quality streaming. Yeah, that's why I really want to get the... Oh, that is not even that much further zoomed in. Okay. We're just increasing the zoom level. Okay, there we go. Yeah, I really... Yeah, I don't have those. I don't have those OBS skills. Yeah, I know, right? So I actually saw a couple really cheap. So I'm putting on these parts, and oh my goodness, that focus is miserable. Okay. Let's see if I can get this sharper than the autofocus. I think I did. No, I didn't. Anyways, I really want to get that USB microscope. I was kind of on the fence because for our previous streams, I feel like it's been going okay with like the manual microscope zoom stuff. But today I'm just not seeing it. Here's what I'll do. I'll make a point. I'll bring it closer down to the bench. There. Manual zoom. Okay, back to it. Okay. So, anyways, so these are a lot like the other Meanwhile supplies, where it's actually unregulated on the high voltage side. It's just doing fixed duty cycle switching of a power supply with assumptions. And for what we're doing, that's fine. We don't need absolutely accurate voltage on the high voltage side, except for the 3.3 volt rail. And so basically, that's what we do. We just have an unregulated, approximately plus or minus, I think it's 8 or 9 volts supply. And then we regulate one of those down a little bit further to generate, yeah. Yeah, absolutely. Absolutely. Next time we kick this off, I will have that USB microscope. It was one of the ones that can actually sit on the stand too. I was getting pretty excited looking at it. Because we had one of those little handheld ones that are like $20 on Amazon. And it just didn't quite do it for me. So we're gonna go up a notch. It's got like the 7 or 8 inch touchscreen and the HDMI output, so we can get another capture card hooked up to the PC, and yeah, it'll be sweet. But we got the digital isolator installed now. I believe we have the analog temperature sensor. We've got our current shunts, a couple transformers, and this is pretty well done. Temperature sensor. Yeah. There's nothing like a new tool day. Maybe we can do an unboxing or something for it. Just do a little comparison of how it was before. With the manual zoom to current shunts, we're still using 200 milliohm in parallel for a 50 milliohm shunt. Oh yeah. Using leaded solder. At the moment, yeah, I'm being a little lazy. I'm using leaded solder. I've got the unleaded stuff, but it just doesn't flow the same. It just doesn't. Yeah. Okay. But yes, we are using OBS. I forget if there are other streaming softwares, but OBS is pretty fantastic. And you can't beat the price. Alright, I'm going to get this placed. It's basically the same, even though it's a little transformer. It's not fundamentally different than any other surface mount component. Okay. Oh boy. Oh, I forgot I put the temperature sensor on there. I don't think I'm ever going to find that again. Oh, there it is. It's right next to the board. I am lucky today. Okay. So, unfortunately, I put the... well, by design, I put this temperature sensor on top of a giant ground plane. Let's make sure you can see that. Yeah, I put this temperature sensor on top of that giant ground plane right there. And basically that means that soldering it to the board is actually pretty difficult without preheating. That ought to be enough just to take the edge off. I'll come over here. It's like you try to solder to the pin, but it's connected to such a large copper plane, it just sucks the heat out, and you don't really have a chance to. There you go. It's placed. Okay, excellent. Coming over to the other side. Knocked a lot of the solder off. We really don't need much to get this part on. We really don't need much. I'll just come over here and alright, that is plenty for the 3 pads. Oh yeah, preheating is super important when you're doing like thermally imbalanced work like this. I'll just come back and touch up that first pad. Didn't have any flux. Sweet. So now we've got our temperature sensor installed. Oh, if I remember correctly, I thought I saw a rework. The temp sensor, what are we using? It's on the schematic, but I'll pull it up. I'm using the MCP 9700 AT. Get this on the, yeah, right there. MCP 9700 AT. It's a pretty good part. And if I remember correctly, I programmed the threshold wrong. I was staring at the schematic one day, and I was like, this doesn't feel quite right. This doesn't seem right. And after further inspection, I realized, oh yeah, right. I forgot the 0.5 volt offset that sensor has. Mm. Thanks, David. It's better than unleaded. You get cold solder into the unleaded stuff? Yeah. Years after you solder. Yep. Yep. Thanks, David. I think I'm just lucky. Either that or I'm getting good practice. But yeah, that went really smoothly. That went really smoothly. Um, the part number. Yeah, I already did that. All right, sweet. On to the next thing. These. Now, hopefully, I can still live up to the great soldering with these resistors. These are always a trick for exactly the same reason. Just absolutely massive amount of heat required. I'm just putting a tiny little bit of solder on there. And we're going to need a lot of flux. I don't remember which way I found most successful. I think... So if I were... I used to actually keep solder paste for exactly this purpose. But what I found is that it wasn't always the best move, because solder paste expires pretty quickly. And you... Oops. And you need to keep it refrigerated. Something's happening. Oh. Apparently something's going on with the... You guys... Is the stream working well for you guys? YouTube says something's going wrong. Test, 1, 2. Seems like we're still live. We dropping frames? Oh no, we're dropping a lot of frames. Computer. Okay. Glad it looks good for you. It says I'm dropping 10% of the frames I'm trying to send. Ruh-roh. As long as it's working for you, it's working for me. What was I saying? Something about... Oh, man. So I've had really good luck with MG Chemicals in the past. My favorite flux that I used was the MG Chemicals paste flux. That stuff was awesome. I used it about, I don't know, 2 years longer than its best by date, and it was still going strong. It's not a flux pen. It's a little different, but it serves the same purpose. So that would probably be my recommendation. I think MG Chemicals also makes flux pens for soldering. I would trust those just because I've used a lot of stuff from that brand. Generally, if I need a chemical and I want it on Amazon, MG Chemicals is the way that I go. But I think if you get it off DigiKey or Mouser or anything like that, I'm sure they have those supplies on there. Because I've bought, even down to like stickers to label boards as static sensitive, I've bought all kinds of stuff off of there. And if they sell it on like Mouser or DigiKey, you can be pretty confident that it's going to be a decent flux. Sweet. I'm glad that it's working. Probably just had a little... And this is taking a long time. Maybe I need to bump up the temperature on my hot air station a little bit. Oh yeah, there we go. You can see it starting to melt. I don't know if that's causation, but that is some strong correlation. Okay, I'm just gonna... A little bit of flux in there. A little bit of heat. What is going on? There we go. Getting it. Oh, there we go. That is perfect. Okay. On to the next one. Probably put a little bit too much heat on that. Definitely put way too much heat on that. I was getting a little perfectionistic with the alignment. Okay, yeah, this one's starting to go as well. Okay. These don't look the greatest as far as solder joints go. Yeah, the thing that's great about I can smell the rubber getting hot underneath this. All right, we'll give this a little break. I need to get this off the ESD map before I wreck it. Let's pull the. You guys will recognize this. Ugh. I didn't think we'd need that much heat, but I guess we do. Let's see if I can move this without burning myself. Yep, there we go. You guys recognize this? Told you I was settling in. Got the old... Got the old, what is it? This thing, the old computer side panel. Distracting you from work? I don't know. I'm having fun. Usually takes a little bit longer to stream and do it, but it's really about the journey. It's about sharing it with you. It's not just about how much I get done and how long it takes. I'm having fun with you guys this morning. Yep, so David, these are the shunt resistors that are used for current monitoring. I don't know if you can see the Kelvin connection that I've got coming from these to use them in parallel. Basically off the top corners of each of these pads, there's little traces that come out, and then they're actually routed as diff pairs that come over to the primary current sense amplifier, and we're using an OP07. I think it's a Texas Instruments OP07 to do the actual monitoring. There we go. So, yeah, basically, man, getting that off the net worked a wonder. Oh, we still got one more. And then this is technically optional, but I'm just going to save myself from me. Basically, this is a protection diode that will, if I happen to connect the wrong polarity, it should blow the fuse and save the big important FET. Not that, I don't know, I'm not really convinced we could blow it up by putting a giant surge of current through the body diode, but I don't want to find out the wrong way, or the hard way. And this is kind of an interesting story as well. So these, this connector here is made to mate with a pretty small, low-profile set of through-hole pins. And I grabbed these in particular because I checked the website for, I think it was Samtech. So I went and got, like, the Rolls-Royce of these connectors. And basically, oh man, I just snapped it. All right. And basically, what I have to do is I have to push all the pins through because I got like a low-profile 7mm connector But the mate that they put on their website is made for a standard height header. I was a little peeved. I was like, the whole point was to have a 7mm stack to match with our screw terminals, our press fit screw terminals, but yeah, guess not. Not today. That's alright though. Interest in digital electronics? Electronic, let's see this. The computer side panel would be as a heat sink. Electronic loads are cool. I made one somewhat decent. One of the first prototypes burnt with a mistake on the PC. Oh no! MOSFET went boom. Didn't put any fuse. Oh man, fuses help. That sounds like an incredible story. I'm gonna guess that's renowned? That's probably super wrong. I do have some interest in digital electronics. Like, you know, some things about digital electronics I find more interesting than others. I think that's true of anything, really. For example, I don't find like making little what's it called, like Raspberry Pis, like implementing one of those boards to basically recreate a Raspberry Pi. I wouldn't find that super interesting, but that's more of just it's been done 1,000 different times before, and less of a, you know, it's nothing really against implementing a microprocessor instead of a microcontroller. It's just, it's been done a lot. I'm not really sure what value I would add doing that myself. But things like microcontrollers and like implementing USB and stuff like that, I mean, yeah, I find it interesting. For sure. One second, we'll be right back. Alright, sorry about that. But at least the momentary pause reminded me that I was off camera. I was off camera. Okay, here we go. Yeah, I was just putting a bunch of heat into this board to get the diode installed. Alright, that ought to get it done. It's not the prettiest solder joint I've ever made, but I think it just might work. Reno. That's fun. Digital logic. Oh, I see. Like more like FPGAs, or probably what used to be stitching together 7.4 series stuff. Alright, that is our last surface mount component. So I'm gonna get this gigantic plate out of here. Last surface mount component that requires the hot air gun. So put this off to the side. Yeah. Excellent. Excellent. Little coffee break. Little coffee break. Okay. So, anyways, what I was saying before about the connector, this will make more sense later. I might actually save soldering this header in later, because I won't really know where to adjust these pins to until I get the mate. So I'll just set that off to the side, and hopefully we don't break that one. But in the meantime, what we'll do is we'll add the fuse. And now this is something where, oh yeah, I don't know if we've talked about this. Please, if the QAI, please, if you can give me the phonetic spelling, oh, I would be so thankful. There's a few folks. Yeah, it's a struggle. It's not your language. But anywho, anyways, we're we're gonna do the piece of this that I think is gonna be the most different between this and the community edition. I don't know exactly what the community edition is gonna look like, but I've got some big dreams for that. Just because I think that electronic loads are pretty awesome. They're really not that complex to make, but at the same time, they're super useful. And when I was looking to buy an electronic load, half of the inspiration for this project is that I went to buy a decent electronic load, and it jumped from like $50 pieces of, well, basically garbage, all the way up to like $500 really quick. And I was like, well, there's got to be a middle ground in here somewhere for like a $100, $200 decent electronic load. And I mean, I gotta say, I think I found it because I built myself a $100, $200-ish electronic load. So it's just kind of sharing that ability to get a tool that you can trust for a reasonable price. Maybe it already exists. Maybe I'm just missing it, because there's a lot of stuff out there on like eBay and AliExpress and all that. Maybe someone's selling decent electronic loads out there, but I didn't see one when I was shopping. But at any rate, one of the key differences is going to be the current shunts. I wouldn't want to use these kind of oddball sized things from Vishay. I'd want to use something like 1206 or 2512. And what I did for we needed to add a little spacer, right? Because the intention of this project is to use a standard CPU cooler. And basically what that means is I need to put 2 of these copper shims between the circuit board and the part in order for the MOSFET to have the right height as what would normally be found in a CPU cooler. I don't even know how necessary that is, because a lot of CPU coolers have springs and other mechanisms to tighten them. But I realized shortly after designing this, was still wrong. You in turn. All right, I'll try that again. Oh man. I'm not sure. The K-I with the I sounded like I. Key? Kai? Oh, I see. Like. Oh man, I don't know, man. I'm closer. So we'll get this connected pretty soon. And basically, what we're doing with the thermals, I'm getting distracted here. That's okay. The thermals are going to be transferred as normal through some of this layered material. I'm just going to cut this little strip in half. We're going to use that to get the heat up out of the... this is basically to thermally couple... Alright, I'm reeling it in. This is to thermally couple our MOSFET to the PCB. And the only real reason why that's important, it's not really important for heat sinking. And this is an incredibly large amount of this thermal material to use for not heat sinking. But basically it's just to ensure accuracy of the board temperature. This is to closely couple the PCBA to the package temperature of the FET. And that ends up being super, super important, because that's our over temperature protection, right? All our over temperature protection understands is PCB temperature. It has no concept of MOSFET temperature. So if we don't do a good job of thermally linking the part to the PCB, well, we are losing out on a lot of the benefit of this over temperature protection. And there are actually standard, I had to cut these with a hacksaw is just kind of a waste of time. And I love you guys, but I don't know if I want to go and cut a bunch of 1-inch squares of copper just to make a community edition electronic load. So I think what we would do is they've got like standard 20mm by 20mm pre-cut like copper shims. I learned this after the fact. We'd probably use those instead. Like a strong probably, like near definitely. Okay. All right. Just getting this lined up. I should zoom out because I am doing a terrible job of framing this. There it is. Okay. So now this is where it gets kind of crazy. Because now I need to try to like apply pressure to keep all those shims in place. This is not a great way to assemble this. Yep. Uh-huh. Super not great. That's alright though. It'll get the job done. Oh. Need to boost up the temperature. So this is super, super critical part of the assembly. You can tell from the focus and the silence. Oh, there we go. Okay, so there's 2 pins kind of tacked in. Let's see if I can get this third one. Oh boy. Yep, that was my finger. Don't do that. Don't touch your finger with the soldering iron. Alright. Thankfully, it's just a glancing blow. I didn't really get myself. I promise. I'm okay. Okay. I'll give it a try. Give it a try. So it's like... Can I see her? Yeah? Maybe? Alright. Yes. Alright, so thankfully, looks like the copper shims stayed roughly in place. They're not, like, cemented in place, of course. But the beautiful thing about this thermal material is that it melts and it flows. And so once we get this thing actually tightened down with the final heat sink, this will be very much secured in place. And this is actually ready to go. What I'm going to do is, like I said, I forgot to tweak the range. So if you look on the schematic, you'll see that this jumper is supposed to go between 70 and 90 degrees C. But I'm pretty sure that if you add the 1/2 volt, what you'll notice is that if you short the 90 degrees C jumper, it comes out almost exactly to 75 C with the 1/2 volt offset. So I'm just going to short that. It's not actually setting it to 90 C. It's setting it really, really close to 75. And I truly, truly promise that I'm okay. Okay, so that is the daughter card. The daughter card is ready to go, but unfortunately, it's not going to do as much without something to plug that into. So I need to duplicate the process for the main board. The main board is quite simple, however. All we really need to do is install this jumper. We need to install the connector, which allows for using the ATX power supply. Hey, shout out to everyone who found the stream last week and was a part of the testing where we tested the Ripple load performance and just made sure that it would work correctly for our application. It was a pretty fun stream. But anyways, that's where we plug in that ATX, standard ATX computer power supply. And then we've got the option to add some bulk and some fan connectors, USB connector. It's really just connectors. There's not a whole lot to do. Before we solder any of this stuff in, though, here's what I think we should do. I'm going to grab the box of mainboard components. We're going to start getting this ready because we've got some press fit connectors to put in. And now there's a lot of ways that one could put press fit connectors into a board. And by that, I mean there's one right way and a lot of wrong ways. You would use something that's basically an arbor press. And an arbor press is something which allows for very straight linear motion, and you can just like clamp down on something. They are absolutely fantastic. Arbor presses are great. I don't have an arbor press, so what we're gonna do is basically lean on. We're just gonna kind of use a screw from a standard clamp, and that also will do something. We need a couple of these RGB connectors. All right. Can you tell I'm getting excited? I'm just like, let's go, let's go. Just burning through pulling these parts out to get this assembled. We need 4 of these connectors for the daughter cards. We need 1 of these for the UI. And 2 of these to connect the 4 channels of the electronic load. We need a boatload of fan connectors. How many do we need? We need 8. Alright. 1, 2, 3, 4, 5, 6, 7, 8. And then I'm going to do 2 of the PWM enabled. It's like if I need to plug in a pump controller or something, this will just fix it to 100%. For if we get the water cooling hooked up. Then let's do like 2 of these capacitors per rail. So we've got a 12 volt rail, got a 5 volt rail, and a 3-3. Oh, that worked out all right. And that is all of them. That's all of the parts that we need to finish the main board. They're all pretty big, pretty easy. I think we'll fly through them pretty fast. And we've got a few of these press fit connectors to put in as well. We've got 4, 6, 8. 8 of these. These are the same terminal blocks or the same press fit power cubes. This says red cube, 8-pin. These are awesome. I love these things. Just lets you pull like 100 amps out of your circuit board. For your electronic load, it tells how much power it can eat during a long duration, still have a decent temperature, and they're doing it good as cuts. Oh, yeah, that's fair. Yeah. Yeah, I mean, this isn't really the part temperature, but yeah, so this is actually all enforced in hardware. So there's basically a hardware protection circuit. If I'll jump in and I'll walk through this a little bit. So you see I've got this little I've got a little OTP LED, a little over temperature protection LED. When we look around near here, you see there's also an over voltage and an over current protection LED. And so if you go over the hardware current limit, then there's a different software current limit. But if you go over the hardware current limit, it just like sets the FET gate to negative 8 volts. So it just slams the MOSFET off as hard as it can. Same for over voltage. If you apply too much voltage on the input, it just turns the FET all the way off. And that can only protect it to a point because, of course, if you exceed the voltage rating too much, but at least it won't allow the part to dissipate power if you're applying too much voltage. And then the over temperature is exactly that. So the micro can't read the body temperature of the parts, but at least you can know that you can never damage a part. So the software just detects when something is wrong. Yeah, it works, so it's fine. Fair enough. Fair enough. In this case, you can detect that one of the protections has kicked in simply because you expect the system to be dissipating power, and it's not. So that's pretty much, when you set it to do something and it doesn't, that's a pretty good indication that one of your protections has kicked in. And this is going to be a little messy. You ready for some cringe? Because I know I'm about to. So basically, all I'm going to do is take this clamp, and then you need a little something to make sure you're not pushing on the pins on the back. Kind of get it aligned, and just turn the screw. And yeah, this is not great. Oh man, I am failing super hard. I might need to do this off the bench so I can keep the thing flat. Not sure how well I'll be able to capture this on the camera. If I'm feeling super motivated, I'll get some awesome B-roll for the summary video. Yeah, this is actually really hard to... I almost wish I would have done this off stream, done this as prep. This is really kind of difficult. Oh boy. Okay, so basically here's the struggle that I'm fighting. I'll walk you through this because you can't see it too well. I'll do it with my voice. Basically, as I'm trying to pull this in without an arbor press, and this is why you'd want an arbor press, basically with an arbor press you could just have a die. And what that die would do is it would cradle the circuit board and the component in a way that makes it really, really easy to push the component in. And it would make it easy because it would hold it all in alignment and keep it all nice and square and allow you to apply even pressure across the top surface of the part that gets it inserted in the circuit board. That is why the arbor press is the right tool to use. And basically what I'm doing by using a clamp and freehand pressing this into the board, basically I might be applying uneven pressure, which could either push the part in at an angle and embiggen the hole in a way that will reduce the current carrying or perhaps damage the circuit board, which is why it's absolutely not recommended to do it this way. But yeah, basically that's what you're risking. And I'm really struggling to keep this thing lined up. So you can see I've got 4 of these halfway in. They're not quite fully down, and the reason why is just because I was finding it incredibly difficult to do that with the spacer underneath to fully actuate them. So we're going to do this as kind of like a 2-step thing. I'm going to get them kind of nudged into the hole, and then I'm going to actually finish pressing them in. This is bad. Don't do this. Buy an arbor press. Arbor presses are just kind of expensive. But lesson learned. I think we did this in the past as well. I think it was just a pain from the past, so it didn't hurt anymore. But now that I'm feeling it again, yikes. Add that to the list of tools to get in the shop. Arbor press. Hello, Dave. You know, I'm gonna guess. I'm gonna say that's Michael. I actually didn't make one of laying out these boards. I think we made some pretty in-depth. Someone correct me if I'm wrong. I think it was the UPS project. I was doing very similar things. I was doing high voltage PCB layout that had creepage and clearance requirements, and basically what we did is we just walked through. I used a tool called Saturn PCB Toolkit, which references some IPC standards, we use that tool to determine the trace widths and spacings required to maintain that isolation. Oh, come on now. Oh, this thing's driving me nuts. Okay, we're gonna flip this around. I think this is gonna work better this way. So now what I'm doing is I'm setting my spacer on the top of the board, and we're gonna put the clamp around it. But yeah, so I didn't on these boards, and perhaps that was a miss on my part. What I saw is, I try to keep things pretty fresh on the channel. I try to not do too much of the same thing. And so when I'm doing something like PCB layout, it gets kind of tricky to keep it fresh and new, because it's really kind of the same thing over and over and over again. So I will take that as a, I'll go back and I'll watch that video, and I'll just see if I think there's anything we can add to PCB layout. Maybe we can take it from a different angle, or speak about it in a different way or something. But yeah, good to know that you're interested in learning more about how we made these boards. So we applied the same principles. That's kind of what I'm getting at. We applied the same principles of high voltage PCB design, creeper clearance, isolation. Applied all those same principles to this. Oh boy. Alright, we're almost done. We're almost done with the clamp. The weird clamp arbor press nonsense. There we go. Alright. There are a couple other comments. It is really hard to read them when I'm upside down holding a clamp and trying to not crack this circuit board in half. Yeah, I'll admit, this feels kind of insane. Yeah, and actually, the combination of an arbor press and a 3D printer would be pretty fantastic, as long as I'm dreaming. Just because you could build a custom jig. Whew! Alright, I'll show you what we just did. Didn't crack the board in half. That's pretty great. So now you can see that on this side of the board, the leads poke out a little bit. And then on this side of the board, the blocks are flush. They're flush with the board, where if I show you the other side, there's that gap. We're taking up that gap so the board mates correctly. Okay, let's see. David, welcome, welcome. Got some work to do. Have a great day, Muhammad. Absolutely. See you, man. E for everyone. Work out your homework pronunciation. I will try. I will try. Yeah, so that'll be fantastic. I, for one, cannot wait to get this thing up and running. For those that have been following the project, one of our biggest issues, if you want to call it that, one of the biggest challenges with this version of the electronic load was thermal management. Our previous solution simply was not good enough, and I took it upon myself to try to make that better, and we're trying to use a CPU cooler to accomplish that. And I cannot wait to see if taking fundamentally the same design and restructuring it a little bit, if that's good enough to fix the thermal design of our first prototype. And actually, I feel a little bit bad because with the recent move and everything else, I didn't do a great job of keeping the live streams and the regular content in sync, at least not as much as I would normally like to. And so I felt like there was a really big lag between live streams. And I'm going to try to do better about that, because you're having this, maybe not weekly, but every other week, every once in a while, just to spend some time together on a Saturday, I really enjoy this. And it felt really weird to not talk to you guys for that long. I know in our last stream, we had an awesome idea to recap. I think this was from Dave, to recap one of the ATX power supplies that seemed to be malfunctioning last week. And perhaps what we'll do is crack open the supply today, just take a look at what capacitors we need to buy. Then maybe a couple weeks down the road we can do something similar and just tack on a little bit of recapping it, making sure that the ripple was reduced. Oh. Not quite there. Almost got it. Almost got it. Okay. Come on now. All right. That looks about right. One more left. There we go. Press fit. Whew! Sorry about the cinematics on that. Yeah, hello. I'm gonna try. I'm feeling bold. It's like Santiago. Oh man, all right. I'm working on. This is actually a 4-channel electronic load, and what I was working on in that particular moment and doing a miserable job of filming, we were putting in these press fit connectors in a way that one should never install press fit connectors. We were using horribly inadequate tools to install that. But basically the intention is we've got these electronic load front ends, which we can screw down into these blocks with, where is it? It's right here, with a few of these connectors down here. So basically this slots in, gets screwed into this board, you add a computer cooler on top, and it should, in theory, stay nice and cool. So we're finishing up the assembly of this prototype, and then we are going to test it out. An ESR meter, like an LSR meter for like measuring the parasitic ESR of a capacitor. Don't have one of those. Okay, all right. Took us so long to do that. My soldering iron went to sleep. We'll get a couple of these capacitors installed. I think I'll put one of these over there. Put the 12-volt ones right there. Let's put the 5-volt one. I don't remember. I think that uses 3.3 over there. So we'll put the two 5-volt ones over there. Second 3.3 over there. Let's push these off. Excellent. So we're kind of bouncing all over the board. I'll zoom in if we're focusing on one particular spot, but right now this board is absolutely massive. We're just adding these in. So in the previous stream, basically what we did is we looked at the ripple of the power supply that we're about to connect to the circuit board, just because I know that most modern motherboards for computers, and that's what we're using a computer power supply, most of them don't really use, to my knowledge, the 3.3 or the 5 volt rails very often. They very often, for sensitive components, regulate their own supplies. And so I think they do that just to abstract themselves a little bit from the ripple of the primary power supply, which makes sense. Like, they wouldn't want somebody to install a power supply and have it all of a sudden not work. That would be kind of a problem. But these capacitors, since we know that they're using switch mode power supplies, allow us to reduce the ripple just a touch. In this case, we added up to half a farad of capacitance on each supply, which should help us to significantly reduce the voltage ripple on our board. Based on our measurements, though, I don't think we're going to need all of that. I think we will be doing just fine with significantly less capacitance. And that's why we're only installing 2 of these electrolytic capacitors. There we go. These are, like most other surface mount components, they're being soldered on in a, what I would say is a pretty standard way, where you tin one lead of the part, or rather one pad on the circuit board. Then what you do is you keep that pad molten, kind of slide your component into that solder, and then touch up the other lead. Alright, I think, let's see, I'm going to try to get this aimed a little bit better. There we go. Hopefully you can see that. How much peak-to-peak ripple did we measure? So it actually depended on the supply. The peak-to-peak ripple, on the worst supply, the one that we want to recap, on the 3.3 volt rail, we measured like, oh, what was it? Does anyone in chat remember? I think it was like 900 millivolts of ripple. It was absolutely insane how much ripple we measured. I was shocked. But most of the time it was a lot more reasonable than that. So that was a case where we can be pretty confident that the system was not behaving as designed. Like, it was a pretty old supply. The electrolytic capacitors were very likely drying out. I'm going to try to get these fan connectors installed. Oh no, there we go. Okay, and that was just using a little spare piece of FR4 from an old project to maintain some pressure as we spun it around. And these don't need to be laser accurate when they're installed. It is just to provide power to some fans. You'll notice we've got the 4-pin connector or header on the board, but most of the time you really only need the 3 pins, especially for something like this. The 4th pin allows you to use PWM controlled fans and reduce noise, but in this case we're more concerned with getting the heat out than keeping the noise down. Alrighty. So yeah, I don't think most of the ripple was nearly that bad. On the supply we're using today, it was maybe 20 to 30 millivolts of ripple on the supplies. That's nothing that I would really be concerned about. Even for our microcontroller, that should be okay. This is a reasonably modern ARM core, and much like the computer processors, they actually usually run their core at like 1.8, 1.5, something around there. Like you can adjust the core voltage, and most of them are starting to have regulators built in to accommodate that, which is pretty bizarre. At least from a, where we used to be a few years ago, right? Microcontrollers used to all be 5 volts, and now we're getting to, they're having to engineer in compatibility with 3.3 volt logic to some of these parts because the core's not that voltage anymore. That comes down to a function of wanting to run faster, use more modern silicon technology. And as the transistors shrink, they just don't handle as much voltage. Okay. Fans are installed. Yeah. The fixed daily, this is just a 4-layer board. And a part of that is why this thing looks kind of crazy. The layout is not what I would call ideal. In part because we did a trade-off of, with JLC PCBs SMT service, they can make boards with more layers, but they won't assemble them. At least not when I ordered these. That seems like something that will likely change in time, but at least when we got these built, that was not the case. And I'm tacking in these connectors. Do the same next two. And you can see that these connectors were carefully selected such that the height of the terminals, or the screw terminals from Worth, will line up with these 0.1 inch headers. It's a shame that I couldn't use like a standard header to connect these, but I think it'll be well worth it in the long run, just because it'll fit together really nicely. Gotta say, through-hole soldering is almost therapeutic after wrestling with some of those surface mount parts on the other board. And actually, you know what? I was going to say ideally I'd use a thicker solder. I don't know why I'm saying that, because I've got it right next to me. The difference between the different sizes of solder ends up coming down to the amount of flux present, where the reserve of flux tends to be a little bit, more. I wasn't supposed to touch the ones on the end until I got a couple more pins soldered. But basically there's a little bit more flux, so you just don't burn as much of the wire, and you have an appropriate amount of flux for the solder joint. Helps to let the solder wick down into the holes appropriately. Awesome. Yeah, unfortunately I don't have a spare computer case here today, so we're going to be testing this just on the bench. No worries about that though, because as always, we're working on a static safe workstation, which is not conductive. It's static dissipative, which is often confused with conductive, but it is in fact non-conductive, so you can safely power on electronics at an anesthetic workstation without fear of damaging it with an electrostatic discharge or shorting it out. I'm going to come over here and solder the UI connector. We're down to the last couple parts. All we need to do is get the microcontroller installed and power into the board, and whew, we are off to the races. And I even pre-programmed the micro, so it should power on and be, assuming we didn't make any mistakes and the code's all good. Shameless plug for the Git repo and the folks that have volunteered to help us work on it. You guys rock. I've had a couple people reach out, pretty passionate about helping us out with maintaining the code and improving it. So thank you. Thank you so much. And look forward to seeing what happens to this project. All right. But as long as that's all good, we should be able to power this on. And in theory, the way that I made the code is that it should not be fundamentally different. Like, all the logic, which actually controls this electronic load, it does not matter if it's a 1-channel electronic load or a 4-channel electronic load. It should work exactly the same. It's running the same logic. It just instantiates n electronic load front ends when it boots. So in this case, we're telling it to create 4 instances instead of 1, and we're compiling for a Teensy 4.1 instead of a Teensy 4.0, but in theory, it should just work. I think we're done with the flux pen. Alright, flipping this around. Need to make sure that we install this connector the right way. There it is. We need the USB connector in there as well. Okay, USB connectors in there, the power connectors in there. We might need a little bit more heat to get this in. I'll boost the iron. And what I mean by that is set the temperature like 20 degrees hotter, just to help the tip keep up with the large power planes connected to some of these pins. Yeah. Excellent. Now that I'm here and I'm soldering, it's coming to mind that I don't currently know where our resistors are for capturing the transient response with the scope. That might be really fun to do today, so I'm hoping they're in the toolbox right behind me. But if not, we might need to save that for next week. That would be really sad, though. If nothing else, we can get the DMM hooked up and capture like the regulation performance and the accuracy to the set point before we build in any calibration or anything. We're still kind of in the same boat there. We haven't implemented any calibration routine. So it will just be getting the raw accuracy of the hardware without any software mitigations or any software improvements. And we should be able to connect this to the computer and pull in the information there as well. All right, there we go. USB port is in. Suppose the screw terminals are pretty important. Why don't we go ahead and add those? There we go. Oh boy, these have got a big copper plane attached, and you can tell. Come on now. Okay. Oh, one more. Let's do a quick sanity check as we're preparing to power this on. Let's do a quick sanity check. Let's just take a look at everything that we've installed. So we've got the 4 daughter cards. These holes are to mount this to a computer chassis. Daughter cards look ready. We've got the screw terminals installed. Do I have a Sharpie down here? I'd love to get this a serial number. I don't think I've got one down here. That's all right. We've got the USB connector on the other side of the board. We've got the USB connector installed. We've got some capacitors. Oh, micro is important. All right. Let's install the micro. Then we've got the RGB headers, which may or may not work. That's a new part of the circuit. And then we've got our UI header. So let us install the micro. This is truly the last step for the main board. Got one more connector to add onto the daughter card, and that is the like I/O/communication connector. And I'll walk you through why we save that till the end. I bet I can zoom in on this. We're kind of in one spot. Yeah, there we are. Oh. That was crazy. The iron just went back to the normal set point. Got rid of the 50-degree boost. I immediately felt the difference with these through-hole pins. Immediately. For the curious, I usually keep the iron set to about 350 when working with leaded, occasionally boosting up to 400. Usually keep it a little hotter for lead-free. Alrighty. Done is done. So this is what I wanted to show you before, and didn't really have the main board to show you. See, we built this beautiful method of connecting these, but when you plug in the connector, oh, I see. Sorry. Bad capacitors. Oh. Fixed daily. It looks expensive. It wasn't too expensive. It was all right. It was all right. It was worth it. Let me put it that way. It was worth it. Yeah, I was burning through that for a moment. I'll come back to chat. Hello. Hello, hello. So EE stands for electrical engineering. That's what it's meant for. Electrical engineering for everyone. We're definitely like a mentoring focused channel, or at least I truly like to believe so. And so really part of the intention here is I just like to put information out there so people can learn and really just break down some barriers to knowledge just by showing how much you can learn from doing projects, learning experimentally. Yeah, electrical engineering for everyone. Bad capacitors usually have large ESR. Oh, yeah, yeah, yep. That's absolutely correct, David. And also, yeah, the name. You're correct about that too. Dave, yes, I did code in Python. I do have enough ventilation there. But I'm soldering more than 10 minutes. I have to take a break. That's fantastic. Yeah, there's pretty good ventilation here. Yeah. I'd like to get a smoke heater. Actually, in my apartment a while back, what I actually did is, well, for better or worse, I had like one of those bathroom ventilation fans. I had something that would sit on the desk like right in front of me, and it would just suck the air through some ductwork and blow it out the window. That's fantastic. Um. Oh yeah. Yep. Yeah, David. Yeah. So the thing that I've heard about soldering with this thing connected, I've heard that if you're really unlucky with the micro, yeah, I wouldn't recommend doing that either. David, I completely agree. Don't do what we just did. I've heard that what can happen is you can actually end up wicking solder higher than you would like and accidentally solder your micro into the pins. Yikes. That'd be no good. That kind of defeats the purpose of the whole socket. But yeah, getting heat up there. Yeah, I was just getting through it pretty quick. Anyways, so yeah, this is the problem that I saw when going to install this. I was like, oh great, I bought this header that's made to make the stack perfect, and yeah, not quite. So what I need to do is actually like nudge each of these pins down about half the width. Ironically, it's almost exactly correct that the not gold plated side is almost exactly the right length for this connector. Which is weird because I forget what series of parts I'm using from Samtec, but it's their like low profile 2.54 pitch, and I believe it has about a 5 millimeter plastic housing, and the pins are about 5 millimeters long. And the purpose is that I needed a 7 millimeter stack, and there's a few millimeters consumed by the plastic guide here. And I'll just connect that into the socket. Now you'll notice all the pins are different lengths. And now this is terrible. Don't do any of this. This is not a guide. I'm just forcing something to work that shouldn't necessarily work. And now what I'm doing is I pushed the pins a little bit too far in one direction. And now I'm just pushing them back. I'm seating them fully in the connector, each pin. And then we'll solder this in place to hold it in position. Not ideal, but it'll get the job done. There's multiple reasons why this is not the right thing to do. One of which is something called gold embrittlement. And you notice that when you get connectors like this, very often they are gold plated where the contact happens, and then they're tin plated up at the top. And you might wonder, why would they do that? Because you can do something like ENIG, right? Electroless nickel immersion gold. That's a surface finish that you can get. And if that's the surface finish that your PCB uses, then you're kind of soldering on gold. So gold seems to work, but it's actually a different kind of plating that's very, very thin and barely uses any gold. And what can happen is if there's too much gold in a solder joint, it becomes a part of the chemical composition, and if you get too much gold in a solder joint, it becomes brittle over time, right? Or it can become brittle over time. And so usually they selectively plate the contacts to be gold to reduce the contact resistance, but they keep it out of your solder joint to make sure it stays nice. In this case, we pushed the gold portion back up into the solder joint. So that's not great. They did great work, and we just undid it. Okay. All right, we are getting close. Let us power this on. So, wow, it's time. I guess. Well, we shouldn't quite screw this in for one reason, and that reason is we need to install the CPU cooler. But I'll grab the couple screws and we'll set them off here. And I'll grab the UI. I'll grab the UI and we'll get this connected. Yes, GoTech, you are quite perfectly on time. You came for none of the work and all of the fun. We just finished assembling the board. Welcome, welcome. So here's what I'm doing. I'm connecting all of the daughter cards here. I'm connecting the cable, which gives us control of the system. It's hooked up to the 3.3 volt rail. I have the digital electronics of the daughter card installed. And what we're going to do is a quick ohm check just before we power it on. Because as we all know, this uses an ATX power supply. And when we're using an ATX power supply, the system actually does not have the ability to, what do I want? I want to check the resistance. Okay, so this is the 3.3 volt rail. We don't have like a 1 amp current limit. You know, we don't really have a half an amp current limit. It just gives it everything all at once. That's not really what I would call ideal, because if we've got a short somewhere, a dead short, now that would be fine because it has protection built in. Alright, looks like we don't have any shorts. That's fantastic. So I guess, yeah. Hey, I need to work on my pronunciation. No, I had it. It was like Kaisir, something like that. Yeah, welcome back. GoTech, I'm not sure what I would want to do. If we keep the module as it is, that allows us to change the micro in the future. And if we don't, that means we're kind of stuck with the teensy. Plus, it's a BGA component, which I'm not going to say I can't solder a BGA because we've done it together before on the, what was it? It was the inverter daughter card of the Phase 2 UPS. We've done it before. But it's just really difficult to inspect when you're doing it by hand. And if we were to try to install a sensitive component like that onto a massive circuit board like this, you get into this problem where you've got these tiny sensitive components right next to, there's a very important box stuck in the bottom. I think this has all of our mounting hardware. Yep. And should have a back plate. Oh, really? I thought this used to come with a better back plate. Oh boy. Oh boy. I'm hooked on a daughter card. Okay. So we've got a plastic back plate and we've got a, what is this, a low noise adapter? Oh, this is a splitter, a 1 to 2 fan splitter. We're using the Intel mounting hardware. Oh boy, do I need a manual for this? I hope not. Got a nut driver, got some standoffs. We've got some thermal paste, which we're not going to be using. Got some rubber bumpers. Huh. Let's see if we can figure this out. I've installed this type of cooler before. I would hope that I'll be able to do it again. I think the critical thing is getting the right amount of standoff. And I can't remember if I used these. Oh boy. Oh wait, no, these go on the bottom. Those go on the top. There we go. No. Whew. Okay, I need the manual. I just want to install it correctly. No, Dave, no worries. Oh no, your name got broken. Hopefully that's like in a good way that I pronounced it okay, or I probably butchered it. Okay, so we've got Intel 115X. Apparently we put the little thingies over, and then what in the world are we doing? What? I don't understand. Okay, so we take the plate and we take I, not M, so we want the longer ones, not the wider ones, and then we... What in the world are we doing? Okay, this goes on like that. These are G, not E. So it looks like we're putting these little inserts in there, sliding this over top. Cool. I'm gonna guess this snaps in all the way. Okay, that snapped in kind of nice. This is weird. I remember them having a metal backplate that just kind of worked. I don't know, maybe that's just me. This plasticky nonsense, not gonna say I don't trust it as much, but I don't trust it as much. Okay, so that is installed. Then we poke that through the board. And uh-oh, I might have pushed that into the wrong hole. So it says the furthest one. Yeah, I want to be one back. Okay, so I got these detents to line it up. Getting it. Man, this takes a long time. Okay, getting the static strap. Ooh, we need more thermal interface. And we need to make sure there's got a little protective plastic thing on the bottom of the cooler. We need to make sure to remove that. I'm just going to come down here and cut a nice big piece because I don't think we're going to get this aligned perfectly. So we'll just make sure that we have enough that it'll still work. That's plenty. That is more than plenty. Do you have space for the backplate? Yeah, no. You guys didn't miss anything. There should be space for the backplate. There's 7 millimeters under there, which should be absolutely plenty. So we come underneath. That's not right. This backplate is huge. This backplate actually goes outside of the spec. Because I know I built this thing to spec. And they've got these other things overhanging the board where there should not be things overhanging the board. That's annoying. Does it interfere with the... It does! Alright, I'm mad at them now. I've got other backplates I'm just gonna see if they happen to be compatible. Otherwise, we're gonna need to go a little crazy. Oh no, they're not compatible because these have threads instead of. All right, well, rip this cooler because, well, what you gotta do, I guess. Oh, sorry about that, guys. Sorry about that. Got the camera misaligned. Oh, I'm glad that I noticed that because this is going to be a little painful. This is like a full commit. Can never use this on an AMD system. There we go. That's good. Not going to say... There you go. Now it'll fit just fine. Hey, look. It works. Let's make sure that got us enough clearance. Not quite. Need to trim it back a little more. Those corners are the problem. So we'll come down and just cut them a little bit more flush. Yeah, I wonder why. So their old bracket, the one that's made of metal, used to actually push the alternative bracket like further off the board than this one does, which is a really good idea because, you know, the AMD mounting spec is not the same as the Intel one. All right, that's great. Now that works. That fits just fine. Yeah, so I guess there's space for the Intel backplate, but I didn't make space for the Intel backplate and the AMD backplate. So, I don't know. Guess I'm just weird or something. But at any rate, so they say that what you do once you get that... Wait, what do I do? Oh no, there's two different things I can do. Do I put on the spacer and then the other thing? Or do I not? Where did I just put the instructions? Did I just throw them? Oh, there. Yeah, I did. Oh. Okay. Back to the Intel instructions. Intel instructions. We are not using the extra standoff. We are just using the regular standoff. So we're just putting on these. Oh, should probably put the wrist strap back on. They gave us this lovely tool to use a standard screwdriver, but I don't have a standard screwdriver laying around, so I guess... Oh, there one is. Just use this to give it the extra little tweak. Nope. All right, we are installed. Look at us go. Back plate ready to go. And now two of these mounting arms are what we use. Okay. I guess that's a little different than what I'm used to as well. So for Intel, we need B and... Okay. So we use these somehow. Okay. Yeah, I see it now. This is bizarre. This is super hard. What in the world? So then they say from the bottom, you screw these mounting plates in. Great. How are you guys doing? You guys having fun? Because I'm enjoying it in general. I'm not enjoying the extra steps between installing this cooler and getting the electronic load turned on. I was just kind of expecting to plop the cooler on and turn it on. This is interesting. I wonder why they made all these changes to the design of the Hyper 212. I'm assuming it's for cost, because they went from like a metal back plate to a plastic one, and they went from this like cross-shaped thing to screws that kind of screw in. Made all these little tweaks that, if I'm being honest, don't seem necessarily better. So, just a little curious about why they would elect to do that. But thankfully, now that we've got the back plate installed, we need to get the electronic load plugged in. Okay, so we got all this extra mounting hardware, all this stuff we don't need. I'm going to get this out of our way so we can finish the installation of our cooler. Got our thermal compound, that will become critical. Get these little bits of solder and nonsense out of the way, just don't have any shorts on the bottom side of the board. And while there's no channel really better than channel 1, I think 1 is a great place to start. So let's go ahead and do that. Oh, sorry about that. Sorry, Raul. Sorry, Raul. Oh, sometimes I get lost in the sauce, as it were, and forget that the camera doesn't just follow me. Yeah. Okay, so I'll make sure you can see this, because this is one of the most fun moments of installing a daughter card. Basically, you come in here, and what this does is there's this array of vias around each of these holes, and it just makes sure that we get excellent contact down with the main board. You just screw it down, make sure it's nice and tight. Good stuff. Now we've got the heatsink pretty much ready to go. This is our thermal compound. I do have the coffee. Here. Dave, I hope your coffee's good too. I don't know what you've got. I got a pour over recently, so I've been enjoying that. I've been enjoying that a lot. Okay. Oh, this. Yep. All right. So we got the little copper shims underneath that maintain the standard Intel spacing, which became important, right? Because that's what these standoffs are for. That's what these are for, and they did us the kindness of pre-installing the cooler, or the fan on the cooler, but I need to remove it to screw the cooler into the board, so that's kind of weird. I don't really have a preference. I think this fits either way. I don't feel strongly, but I guess I'm going to say let's install the cooler this way, because this gives us half a chance of fitting 4 of these coolers next to each other. If we do it the other way, it'll never fit in a million years. So with that decided, it's time for the defining moment. I don't know if we can get a drum roll or something, but there's been a lot of work coming to this point. So let's peel off the protective film. Oh yeah, got the direct heat of those You can see the heat pipes are ground to make direct contact. It's pretty fantastic. Gonna start screwing in the 4 points up. Oh, come on. I need a screwdriver. And these get pretty tight. This mounting bracket is pretty serious. There's a lot of force here. I'm not sure quite how far I'm supposed to screw this in. I feel like we're gonna turn this thing into a potato chip, though. This applies a lot more force than the water block did. Probably because it's an absolutely massive air cooler, and they're trying to prevent that from ripping off of a circuit board. I think you're supposed to take it all the way down. I'm just terrified. I'll do it. I'll follow the instructions. Mounting pressure is important for thermal interfaces. Doesn't scare me any less, but I'll do it. There we go. Wow. Now that's a cooler if I ever saw one. Woo! This thing's huge. The screw terminals fixed daily. Great question. They're from Worth Electric. They're the Red Cube M5 8-pin. Part number is 7460305. Hopefully you can see that. That's what we're using. I love those terminals. Okay. So, unfortunately this fan is not RGB. We'll have to get our RGB game a little bit stronger in the future. Sorry about that. However, we can cool it. I am going to put the fan on the other side because right now we've got this beautiful view of the over voltage, over current, and over temperature protection LEDs. So I'm going to put this fan on the other side just to kind of get it out of the way. And this is going to be really cool. Just to see how well it performs. I have not ever tried this before. Do you guys think we're going to get our 1,000 watts? Well, I don't think we're going to get 1,000 watts. 1,000 watts is like pie in the sky dreaming. But we might be able to get like 5, 6. We might be able to get a few hundred watts. That'd be pretty crazy. I'd actually need to make sure that we've got enough. I'm sure I've got them around here somewhere. I've just got a box full of power supplies. So I'm sure we can find... Oh, wait, that's not right. I'm sure we can find some combination of those that'll get us the maximum power. I've got, 300 watts in a lab supply right around the corner. Okay. The fan is installed. I'll turn it just so you can see it. Fan is installed. I'm just going to pull the fan connector over, and this is an RPM fan, so I'll just make sure it turns on and give it the full power. Haha. Okay. Sweet. So that's a slightly bigger cooler than our previous design. All right. Time to get our power supply. You'll recognize this from last week. I'll get this off. to the side. I gotta get some of these tools out of here. Still got the test connector from last week. Get these off. Out of the way. And we're plugging in a 20-pin connector. Supports 20 or 24 pin. Doesn't really matter. We're pulling approximately 1 fan worth of 12 volt power. So I think we'll be alright. Plugging in the supply. I see. We seem to have run into a slight lack of outlet. There we go. And we've got the lab supply coming around. Sure, let's set that right on top of the other one. Okay. Who's ready to see this thing turn on? Because I know I am. Haha. Before we go and actually connect the lab supply, let's just try powering this on for a moment. Uh-oh. I'm seeing one of our rails is not on. That's not ideal. One of our high voltage rails didn't turn on. We need the DMM. Let's start checking our voltages. Oh boy. I am now immediately regretting not doing a more thorough investigation of the different supplies before we power it on. It's probably just 1 pin on that. I think I can still get to it with this cooler installed. Let's just power it on. I got the 5 volt standby up. We got 5 volts okay. We got 3v3 okay. Let's just check all of the rails. We've got, oh, sorry, you guys can't see that at all. So there's the DMM. Let's see if I can tip that for you. There you go. So when we come to check these, we got, should be 12 volts. 11.8 should be 5 volts. 5.3 should be 3.3. Good to go. And what do we see on the display? Oh, beautiful. Beautiful, beautiful, beautiful. Oh, you gotta be kidding me. Uh-oh. I compiled the firmware for the wrong board. That's not super. Yeah, so there's 2 different build options. Whether you're programming a 4-channel or a 1-channel, and I built it for the 1-channel load. So, yeah, we need to fix that. And unfortunately, I don't have that programming cable down here. So I think we need to take a brief intermission. Call it a minute. We're going to step away. I'm going to get the programming cable for that. If you have a layout error, how do you feel about those 20 PCBs? I would feel very sad. I would feel very sad. And which one was it? Was it the plus or the minus? It is the plus that's not okay. Looking at the board, you know what? We'll resolve this before we do the program. Before we get the programming thing, before we take the intermission. Let's get this. It looks like I'm seeing a solder connection that is not great. We'll put a little bit of flux on that. We'll reflow it. Oh my goodness. No, I see what it is. I forgot to solder 3 terminals of the transformer. Oh my goodness. We only soldered the transformer on one side. Oh my goodness. That doesn't change what I saw on the IC. Still looks like one of our solder joints wasn't great. Sure, yeah, let's just solder on this giant heatsink. Could possibly go wrong. Oh my goodness. I can't. Okay. This is not fun. Everything about this is not fun. I should really take this heatsink off, but I really don't want to. Alright, 2 out of 3. Can we get a third? Alright. Yeah, works better when you solder it together, huh? Let's see if we got our negative. Hey! Got all the power supplies now. So I was looking at these indicator LEDs. Hopefully you can see them before. But there's one for the positive, one for the negative side. Oh, I completely obstructed them with cables. One for the positive, one for the negative side. And, oh, looks like we're good now. Yep, works better when you solder it together. That is for sure. Okay, so I'm going to go get the programming cable to fix the firmware on these. Thanks, David. 20 Frisbees. It's hard. We're going to... David, oh, it's nothing. I love hanging out with you guys. I'll admit, when you're streaming all of your... and archiving all of your mistakes, it's not what I would call ideal. But it's all about the journey. So I'll go grab that USB cable, and we'll get this going. Coffee break, everyone. See you in about a minute. And we're back. It's just a USB micro B cable, but it's in the wrong room. I also got a little refill on the coffee. Shout out to Chemex. Sponsor me, please. No, I don't know. I wouldn't even want that. Like, what do I need 4 Chemexes for? I already got one. We're good. All right. Got the refill on the coffee. Fixed an obvious problem in the hardware. Time to upgrade the software. I think I'm going to pop this micro out for a moment. Thankfully, all the rails on the board seem good. We're going to measure the isolated ones just to make sure they're looking fine. Need to program and build. Okay, so I basically just got a pound define for those that are familiar. It's just like in the main program. You just comment in. So, yeah, so this is the dev kit. Yep, that's not right. We're going to do the 4-up controller. Or that's a 4-up is just a way of saying like 4 electronic loads. It's compiling. This is the fun part. Man, we got through all the assembly. We got through all of it. Now we get to play with the control application. Oh, we get to actually test the thing. This is just going to be fun. This is just going to be fun. Okay, it has been programmed. I can now see the comments again. What's the function of those transformers you just soldered? Fix daily. Great question. So basically, the way that this works is there are voltages that a person may want to apply to these terminals that might be considered unsafe. And so one of the things that I do to make sure that the board is safe is I established electrical isolation from the control side to the load side. It's like this heat sink, this daughter card, these traces out here lives in a different electrical domain than the rest of the circuitry, like the buttons and stuff that you touch, the USB interface, all that is isolated from the load. And all of the loads are isolated from one another, which is pretty fantastic, because if you want to apply different voltages from one to the other, that's not really a problem. You can know that they're electrically isolated from one another. So those transformers are putting some power from the low voltage or control domain over to this electronic load's power domain. And so in this way, the power and control are separate. David says, Mark Wien's a YouTuber that goes all over the world and eats food. Always likes everything he eats. He drinks filtered coffee and loves it. I can't take his word for anything. Oh, just like standard drip coffee? Oh man, David, that sounds tricky. Okay. Powered on. Let us take a look at the high voltage supplies. So we've got 8.5 and hopefully negative 8.5. Yep, just about symmetrical. So that means that if we connect a load, it should actually turn on. Just out of curiosity, let's see what the resistance is. Right now, it should be pretty high. Oh, right, that little thing. Okay, so I'll show you what I measured. I measured 0.4 ohms. Sound off in the comments. Hit me with your best guess. Why do you think the load is showing 0.4 ohms? All right, I'll just tell you. There's a lag. One of you is probably right. So basically, we've got a PID compensator, right? And it's trying to regulate to a certain power level. And this is how I knew it was wrong before. Let me zoom in. Basically, So I was looking at this channel indicator, and I saw that I pushed the button and it didn't go to channel 2, and I was like, that's not the right firmware. So basically, if I come in here and I set this to, let's just set this to like 0.1 amp. We're going to hit run. Basically what was happening before is this system, it regulates current. And if you tell it to push 0 amps through the system and there's no power connected, there's no voltage connected, it can never actually achieve like less than 0. So the set point is 0, the compensator just kind of stays where it is. Where if we apply a voltage, well, now we've added the opportunity for it to go above that set point. You plug it in, it applies a little bit of current for a very small amount of time. The compensator says, wait a minute, we're supposed to be set to 0. And then it turns itself off. So just since there wasn't a potential That's not really ideal. I would love to set the set point to negative something, like the quiescent set point to negative something. That might make this a little easier. I'm just going to grab a little bit of wire. We need to put something in the screw terminal that we can clip our DC power supply to. This is 18 gauge wire. So you got to keep it pretty short if we're going to try to pump 10 amps through it. I'm pretty sure this is not even close to the right size for 10 amps. But I'm excited to push the limits. So I guess a few things that we've got in mind today is we want to do transient response, at least to capture it once, right? We don't have to do a perfect investigation. We can always do a deep dive later. Just want to test the power handling. That I want to do for sure. I want to push this thing and see how much power we can dissipate with the CPU cooler installed. And this is no slouch, right? I think we could do much worse for a CPU cooler. Yeah, should be good. Alright, so I'm just gonna put the positive, the yellow wire to the positive, and then we'll put the blue. Yeah, maybe I should have used red and black, or black and anything, just to use a better color, but yeah, that's alright. So now this power is going through the main board, through those screw terminals, into the daughter card, to the FET, back around. I'm going to set our current limit to something pretty small, maybe 1/4 of an amp. We're gonna. Do we want to put the DMM on this? We probably should, right? Yeah. Yeah, that'd be poor form if I didn't let you guys see the actual current. So we'll get this connected over here. Oh no, please don't. Did I leave the banana plugs upstairs? Oh. Well, that's just sloppy. No, I've got these here. This should work. Current. So then one of these will connect to, hold on now. We're going to do low side. Let's do high side current sensing. So we'll connect the ground right to the ground. We'll connect positive. This is going to look weird with the colors because I made these warm and cool colors. But now if I set this to current, here we go. Did I do it backwards? What? What did I do? Set it to 1 amp. It does not seem to be communicating. That's kind of weird. We are not measuring voltage. We are not measuring current. And it seems as though the set point did not make it through. That's pretty weird. Let's check the 3.3 volt rail on the daughter card. She's got a separate power domain. It's worth a check. Ground, power, got a 3.3. Let's just check the digital isolator. We've got, this should be the response back. We've got power right there. Any of these pins? .3, 3.3, 0, 3.3. Let's check those same three on the other side to make sure they're coming to the isolator correctly. Wow, that is really, really hard to get to. That should be ground. Double check. All right, got a 3.3. Going one over. It should also be 3.3. I am struggling to get this. There's a giant heatsink in the way. Yeah, got a 3.3. 0. What? That one should be a 3.3. Yeah, it is. Okay. So it looks like the digital communication should be able to get through. I mean, do we just try a power cycle? Is that our play? Do I go through a couple different channels? Now we noticed something weird. Well, let's just set them all to run. I've only got one of these installed. That shouldn't really hurt anything. But none of these are measuring voltage. It seems like everything is connected, but we're not measuring voltage. That is bizarre. Huh. We are seeing a little bit of current flow. No current, no voltage. Let me just check the firmware. Let's make sure we didn't do something silly. Yeah. So it looks like we're using the pin map correctly. Oh no, camera froze. Oh. Sorry everyone. All right. Thank you, David. We're not stuck anymore. Okay. I feel like this always happens right when we get to the meaty stuff. The stream always gets stuck. It's driving me nuts. Okay. So let's make sure that the voltage is actually making it to the daughter card? Does that make sense? Yeah, let's just double check this. So we should see about 10 volts if everything's connected to this screw terminal. Okay, and likewise, we should see 10 volts if everything is connected here. We see 10 volts. And everything should be making it through the fuse. Yes, okay. So it seems as though the electrical connections are there. We saw the digital logic analyzer making it. Yeah, and see, this is what's driving me a little nuts right now. We tried this same thing the other day. There was something weird going on. So here's what I'll say. Let's try moving this daughter card down to channel 2 and just see if that changes something. Let's just try. It shouldn't, but that doesn't mean that it won't. And oof. I am now immediately regretting installing the cooler this way. Because we can't get to the screws that release the daughter card. God. Ugh. Hopefully we didn't tighten it too tight. I can get the actual bit in there. If we can get a, oh man. This is gonna be... Everyone close your eyes. It's gonna get a little weird. Oh no. Oh no. Oh no. I don't like this at all. I don't like this one bit. Now, there are some... Yeah, we could have kind of a communication issue or something. I don't think we would. Alright, I think I need to take this cooler off. I really don't think that we should because... And for those looking at... Oh, the mainboard schematic. I don't know if we released that, but basically this mainboard schematic is linking the components in almost exactly the same way as it was before. Oh, the fans in the... And Cooler Master, you did okay. But I gotta say, I really don't like the way this cooler interfaces with the... It's like we either have the option of covering up the status indicator LEDs or being able to remove, or needing to remove the cooler every time we need to adjust something. These aren't necessarily ideal choices. So what we'll do is we'll just run this without the cooler. We won't dissipate really any power, of course. Wow, that got a lot of mounting pressure on there. That's pretty sweet. I'm going to set that off to the side for a moment. Yeah, start with the smaller cooler. Yeah, absolutely. There's lots of different Intel compatible coolers, and that's part of the reason why we did this. It was just like this acknowledgement that there's this whole industry of cooling technology. Yeah. So I won't make you guys watch the process of assembling the other 3 daughter cards, but the intention is eventually, depending on how this goes, I'm assuming it'll go pretty well, but depending on how this goes, we're going to, man, this has got some weight to it. I think it's the screws and stuff. The back plate. Just feels awesome. But at any rate, yeah, this is gonna take some serious debug. If this doesn't work today. Oh my goodness. No, wait, this should be okay. I'm trying to remember. I thought there were a few reworks. We designed this thing a long while ago. I don't know. We'll just try power it on and see if this works. So now we're in daughter card 2. Oh, probably works better if we connect the load, eh? To the right. Oh boy, that's a fan. All right, let's unplug that. Okay, so we've got channel 2. We've got the negative. Got the positive. Okay. And now if we check the compensator, I'm hoping that if we look at the gate voltage, we should see it at about 0. Let's see if I can prop this up so you can see very well. So right now we're in DC volts. Dave, try to refresh. Dave, you lost the stream. Oh no. I think we're still here. It says we got a few people watching. Stream health. Looks like we're doing good. Dave, come back. Yeah, this will make probing the circuit a lot easier. Yeah, I gotta say, it's a little weird, but not impossible. Let's just check the gate voltage now. It should be right at, yep, just below the threshold. If we turn off the power supply, I would expect to see that creep up. Yep. So it looks like the compensator's working. Let's look at the output from our DAC. We are right at 0. That's where we'd want to be. Okay, and let's try to turn on channel 2 a little bit. Hey, wait, this is working. Whoa, hey, oh, okay, so that's cool. Maybe there's something weird with channel 1, but I think we're working. Whoa. Because I'm seeing 0.08. All right, I think we've got something to talk about here. Oh, man. Yeah, this is working. Fantastic. How's the... Oh, yeah, it's getting warm and everything. Okay, so it's time to turn this off. Got to turn this off. Got to reinstall the cooler. But it looks like there's just something weird about the communication on channel 1. But channel 2 is fine, so we'll use channel 2. And we'll figure out channel 1 later. Hey, that's not bad. Dave, let me know if you get the error fixed. Otherwise, we've always got the archive. But yeah, it's always great. It's great that you guys can come along for the ride. It makes me sad when that doesn't work. Okay, so now we're going to move our wires from channel 1 to channel 2. Weird. So I know that, so the reason why I went down to channel 2 is because they're actually on 2 different serial ports. And I just figured, hey, if it's a serial issue, this is a communication bug, then if I go from SPI bus 0 to SPI bus 1, or vice versa, I'm not exactly sure which one went where. I just thought, hey, maybe the issue won't follow me from one SPI bus to the next. And turns out, looks like we made it. So I'll need to take a look at the connections for one SPI bus versus the other, because it looks like one is working and one is not. Okay, so now we've got our positive and negative from the supply. We're going to hook the negative right up to the power supply, and then we got the positive one coming over here, and then the super weird black wire that's going to be our positive terminal, and then flip over to amps. Just like me, I am amped right now. Good, Dave. Glad you're back. Okay, what do you guys think? Should we full commit? I would rather see the error indicators, I think. So I think we'll skew it to that. Who thinks I'm going to regret this? I think no matter which one I pick, I would think I was wrong. So, and totally agree on the cross pattern. I took this off like a goofball before. I'm going to tighten it in a cross pattern to prevent crazy stresses. I'll see if I can scoot this further up to get you guys closer to the camera as well. So some might be wondering why I have so many fan connectors. And basically the intention is to maximize the cooling performance of this heatsink. I would love to install 2 fans, one on each side. And if I install 2 fans, one on each side, that means we're going to need 2 connectors for each daughter card. That's where the bank of 8 comes in. The 2 extras then are for water cooling pump and a spare, because you can never have too many fans. Maybe a case fan, I don't know. Okay, got the cooler installed. Thermal compound still in there. Just need to clip the fan in as it was. And then we'll be off to the races once again. Whoop. Alright, one side clipped in. I do kind of like this mounting mechanism they have. Oh boy, I was reefing on the circuit board in a way that seems healthy. Okay. Dope. The cable managed it. Why would they do that? We need that extra ½ an inch. But really, I think we need that extra ½ an inch. Woo, that is... Aye! Stabbed myself in the finger. Note to self, spread those connectors out a little more. Okay. So you got it connected. Power on. Got a 0 amps shown. That's good. Power on. The power supply. Channel 2 config. We're going to set this to 0.1 amps. Go. Ooh! Proto 2 is the best! Sorry if I peeked. But look at that Proto 2 game though! Whoo! For some reason the monitoring's not working, but hey, at least we can talk to it. I don't know what the heck's going on. The internal monitoring, the voltage and current isn't working. I think that's the show communication config, but hey, that's okay. We can still test the current regulation performance because... Dang! That's pretty close to 0.1 if you ask me. I like our controls updates. New daughter card is best daughter card. I like that accuracy. If you guys remember, low current accuracy was like the Achilles heel of our previous design. It's just like the DAC, the 8-bit DAC just couldn't. And so now we are actually using more dynamic range by amplifying the signal with that OP07. We added an extra op amp to amplify it a little more before it got to the compensator. That's helping. And we added 4 more, or we went from an 8-bit to a 12-bit DAC. Let's flex a little bit. Let's go down to 0.05 amps. Okay, that's a little low. It's just must be little too low. How about 0.07? No. I wonder if that's just like, what in the world? What's going on? Did some come unplugged? Why are we not? What happened? It was just working. Alright, let's try a power cycle. Channel 2. Set to 0.1. There we go. Okay, yeah, we're at 0.1 again. Let's set this to 0.05. Why are you angry? It like doesn't want to turn back on. Why do I have to power cycle between changing the settings? This is obnoxious. So let's go for 0.02 amps. Hey, look at that. So we're seeing like a 0.007 amp offset. But when I set it to 0.02, it seems to work. Alright, so I'm wondering if this is just a glitch with my control firmware. It probably is. For those in the Git repo, I'm sorry for being bad at code. I'll get the USB interface hooked up. Hopefully that's working great, and we'll just control it with that. Because I know for a fact it should not require a power cycle, because that makes no sense. So we'll just get the USB interface connected, let Windows install some drivers, launch the control app, and we'll get that going. Was it Kaisir? I hope I'm remembering that right. I love the excitement. I love the excitement. All right, let's get this launched. For Ampere control launching. What COM port are we on? We got assigned COM7. Great. So I'll connect to COM7. The 2-second polling interval. Connect. Come on, baby. Am I gonna get some traffic? Please. Looking good. Oh yeah, I see the data streaming in. Sweet. Okay. And just like we observed, sometimes this crashes a little bit. We're going to set it to current mode. Turn on the load. Should have switched over into serial mode, and it did. Fantastic. The current didn't change. Why didn't it change? Oh, we're on channel 2. That's why. Change channel. Toggle live plot. Alright, so now I can launch the screen cap, I believe. Oh, that's not right. That's not right. There we go. That is what I wanted you to see. Okay. So, now we can actually update the value here, which is pretty great. So you can still see the current as it comes out. And now I'm going to try setting the value from 0 amps to 1 amp. And hopefully it does. No? Why? Why not? Okay. Let's try setting this to 2. What in the world is happening? This thing is super angry with me. Oh boy. Let's try a power cycle. I guess we're just gonna need the power cycle between these. Okay, let's try setting that though. Let's go to 2.5 amps. Let's really start cooking with some gas. Hello? Ruh-roh. I do not understand what is causing this behavior. Let's try smaller current. Oh, that's channel 1. Any thoughts in the comments? Wireless connectivity, that'd be pretty sweet. Yeah, Dave, it's coming together. Wireless connectivity, that'd be pretty sweet. I don't know how I'd feel about that though. Like if your connection dropped halfway through, that'd be kind of bizarre. Okay, so I rebooted. So it's like we can only set a current once. And I can come here and I can go back to config. And I can hit run. Wait, so now it's working. So now if I go and I set this to a different value. So this is like 1.3. Now it works. I guess just don't look at it the wrong way. Alright, cool. So now we're at 1.3. This is how it should have worked before. Let's go for 2.5 amps. No dice. Let's try a power cycle and then 2.5 amps. Better yet, 3.5. Okay, yes, so this was set to 3.51. I'll attempt 3.50. Alright. Sure enough, so we're burning, what is this? 10 volts, 3.5, so we're burning 35 watts. This should be absolutely no problem. This should be easy. I'm going to turn up the voltage just because that's a little too easy. Oh wait, that's down. Wait, what? Started pulling 10 amps all of a sudden. No! Did we blow up the FET? No! That was nothing! And I don't have a spare. That was like nothing! We maybe got up to 50 watts. The only way that that would happen is if there wasn't good contact. Like, if for some reason, like, 98% of this thing didn't have contact. That'd be the only way that could happen. And maybe the bottom isn't very flat, but that'd be disappointing. Either way, we'd learn something. So we got this set to the 200 ohm range. 100 ohms? Oh, that was backwards. It's probably the diode. I don't know. Seems okay to me. Oh boy. Yeah, it says it's stuck at 6 volts and 10 amps. That ain't right. Oh yeah, something's not right. Because when this thing's off, it definitely shouldn't do that. Yeah, it would appear that this FET has gone out to lunch. I guess let's take off the cooler and take a look at take a look at what happened. Debouncing on the switches. I do. That was bizarre. We only got this thing up to like 50 amps and it started to blow up. I'm guessing that when we take off this cooler, what we're going to see is we're going to see a contact pattern that's just around the outside of the FET. Like maybe it's cupped a little bit. I've heard that that can be a problem with CPU coolers. And I know our thermal interface material is very thin because that's how you get good thermal conductivity. So we might need like a more of like a gap filler, or we might even need to try like their thermal compound. But the problem is that I didn't have a spare FET. So if we pull off this cooler and we see it had good contact around the outside and not so great contact in the middle, that'd be a sign. That would be a sign for sure. Could be. There is debouncing, but I also indicate the state. There's a little thing in the upper right that says when it's in like run versus set versus. Oh yeah. Yeah, that contact was terrible. So here's my first sign that something went wrong. This thermal interface material melts. So if it was working, I would see thermal compound stuck to this heatsink. However, it was only stuck in one tiny little corner. And in fact, we dented the heat pipe. Yikes. That's probably not great. And now I look at the cooler. I actually look at the part that was meant to be cooled. And sure enough, the contact is like all around the outside. And in fact, there's like bubbles. There's like bubbles. That's not even close. We need to really... What the heck? Let me see. How do I want to do this? I'm going to pause. I'm going to break this camera off the tripod, and I'm going to get you a real close-up of this. Because that is crazy. Okay. So I'm freehand for a moment. Sorry about that. But here's what we're seeing. Do you see those ripples in there? On that thermal interface material? Yeah, that is not great. That is basically telling me that there was almost no mounting pressure where we needed it the most. We needed the mounting pressure right there. Right where those bubbles are. Right where those ripples are. And they weren't. Sorry, I'm really struggling to focus this. Ah, there we go. Yeah, that is not great. So this FET died because, yes, there was a big heatsink on it, but you can see there was a ton of mounting pressure right there, and not a ton anywhere that mattered. So I think this is not a design issue, but rather a cooler issue. And yeah. Yeah, see how it like melted everywhere that it was touching the FET? That's how this compound works. I just wish that it had more contact area than like none. Okay, well, that's not great. Certainly not ideal. Man, it's been an awesome stream with you guys this morning. I'd love to fix this and give it another go, but that was our FET. We've got more on order to finish the other daughter cards, but that was just left over from the previous build. So I guess we're gonna have to call it there. Just want to say thank you to everyone for supporting EE for Everyone with your time today. Thanks for joining us on this adventure. Sorry about the shaky hand cam. But yeah, it was a ton of fun building this system with you on the stream today. Words cannot even describe how much fun I had today. It was great getting the first test. I can't wait to try the water cooling. I can't wait to see if we can get this cooler installed in a better way so that we can get the air cooler to work on the system as well. Yeah. Self-cooling and electronic load. I'm unsure. I mean, usually they just have a massive heatsink in there, and you can do some sneaky stuff with like switch mode stages and stuff. David, yeah, my pleasure. My pleasure. Thanks for being here, everyone. Thanks to everyone for sharing, watching, anything that you do to support our little community here. I really, truly appreciate it. Yeah, that's about all I got for today. This Proto 2, people. We're here. It's time for Proto 2, and it's happening. It's happening. It's fun. Oh, wow. More to come here. I can't wait to figure out what was going on with the serial bus, why we couldn't control amp 1. I can't wait to figure out what the heck is going on in this system in general, but it's going to be great. All right, everyone. Thanks for your time. Thanks for all that you do. You're welcome, Dave. It's my pleasure. All right, have a great rest of your weekend, and for those people out in the U.S., hope you have an awesome long weekend. We got Monday off, which is pretty fantastic. If nothing else, I hope that you learned something great today, and I hope to see you again soon. So, as always, thanks for watching EE for Everyone, and I hope to see you again soon. Bye.